mathematical proofs are just universal. They can talk to each other. You can use Pythagoras' theorem when you prove that a bridge doesn't break. A bridge, like in architecture, a bridge. So same with our approach, because we can reduce computation in any programming paradigm, any programming language or virtual machine to mathematical proofs. Now we go into a world where there is no fragmentation, the world of mathematics, where mathematical proofs just fit together.
None of the information in this podcast constitutes investment advice or an offer, recommendation, or solicitation by WAGMI Ventures or any of its affiliates to buy or sell any securities. Hey listeners, welcome back to another WAGMI Ventures podcast episode. In today's episode, we are joined by another interesting founder building at the very core of Web3 infrastructure, Professor Grigore Rosu. He is the founder of PySquared. PySquared is the most advanced verifiable settlement layer, uniting all languages, apps, and ecosystems with lightning-fast proofs and consensus. For anyone who is new, this is the WAGMI Ventures podcast, where we do snapshots with interesting builders, founders, investors across crypto and AI. Check out wagmiventures.io to learn more about the syndicate behind the podcast. All right, let's get into it with Professor Grigore Rosu. Grigore, welcome to the show.
Thank you for having me, Benga.
Awesome. Welcome. I'm going to just start with PySquared, a very unique, very interesting name. I think I understand it stands for proof of proof. Can you help us in explaining what that means and how it relates to what you're building?
Yeah, so proof of proof is, so the meaning of proof is more specifically cryptographic proof or zero knowledge proof of mathematical proof. So cryptographic proof of mathematical proof. And it is based on the very powerful separation of concerns principle in programming language formal semantics, which states that computation is deduction. Computation is mathematical proof. So for programming language semanticists, which is my field of research and education, that's what I teach, programming languages and distributed systems and blockchain. So in programming language semantics, once you have a semantics of a programming language, let's say EVM, the Ethereum virtual machine, once you have a formal semantics, now you can reduce completely automatically and very efficiently any computation with that programming language, basically any EVM program execution, say Uniswap or Aave. You can reduce any such execution to a mathematical proof completely automatically. So language frameworks do that for us. And now you have a mathematical proof. This is the first pi in PySquared. The question now becomes, is that mathematical proof correct? And it turns out that verifying mathematical proofs is a lot easier and faster than verifying program executions in arbitrary ad hoc programming languages. So all we have to do now is to generate a cryptographic attestation, a cryptographic circuit, a cryptographic proof or a zero knowledge proof that the mathematical proof is correct. Okay, and now you have a cryptographic proof that the program execution was mathematically correct because it had a mathematical proof. So this is the ultimate argument to correctness, the most powerful argument to correctness, because it's not only ad hoc correctness based on some ad hoc cryptographic representation of the programming language, but it is based on actual mathematical proofs generated from the programming language semantics. And then cryptography only comes to, in some sense, stamp the correctness of the mathematical proof. So in short, it is the ultimate argument to correctness and the most powerful argument to correctness that we as a species, the humans, came up with in the last 5,000 years of mathematics and thinking. Okay, so that's what our foundation is in PySquared.
It's pretty interesting, and I love how you tie it back to how we have evolved just as humans. And I think it also resonates in the mission here for PySquared, where you're looking to solve the fragmentation, scalability limitations that you're seeing in blockchain infrastructure today. Can you help tell us more? I mean, why is this a problem? Why is it important to you? And are there any products you have launched that is banking or actually has already been launched to address any of these problems?
Yeah, definitely. So fragmentation is unfortunately one of the biggest problems in Web3, because each blockchain ecosystem has its own programming language with its own conventions, and developers take a lot of time to learn how to develop in that particular ecosystem, and then things do not fit well together with each other. Then we don't have the right APIs, the right infrastructure, the right interfaces between the different ecosystems and silos. So fragmentation is huge as a problem. And just think about it, because you're talking about humans, and our species. Have you heard anywhere, any time, that fragmentation is a problem in mathematics? No. Mathematical proofs are just universal. They can talk to each other. You can use Pythagoras' theorem when you prove that a bridge doesn't break. A bridge, like in architecture, a bridge. So same with our approach. Because we can reduce computation in any programming paradigm, any programming language or virtual machine to mathematical proofs, now we go into a world where there is no fragmentation, the world of mathematics, where mathematical proofs just fit together. If I need to use some proof of some result in my result, then I use the very well-known concept of a lemma. In mathematics, you can prove a lemma, and then you can use that lemma in another mathematical proof. That would correspond to calling, let's say, a Python program from a Rust program. No problem. That can happen very naturally in mathematics. So by simply going through proof of proof and having mathematics in between, so mathematical proof and then cryptography, at the level of mathematics, think of mathematics as a middleware in some sense. At that level, you eliminate fragmentation. All right, and use mathematically very well understood concepts to put together executions of different programs in different programming languages on different blockchain ecosystems, layer 1s or layer 2s, doesn't matter. You put all this together, and now you have one mathematical proof for which you can generate a cryptographic proof. This is the key. As opposed to having a ZK VM, let's say, which can only give you cryptographic proofs directly for one particular programming language. Now you have another programming language with another ZK VM, another cryptographic proof. How do you put this together? You cannot, because you miss the the middleware, which is the mathematical correctness. So that's how we address fragmentation. Then you mentioned trust. Well, trust comes from trust has many facets. Can be security, can be lack of security, can be private keys, make sure that you use the best cryptography. And all these also apply to pi squared. And we have the highest level of the highest assurance cryptography. We use the best encryption and cryptographic schemes for signatures and proofs. But then there is another aspect of trust, which is that related to correctness. Is that program executed correctly? Or is that program correct? And this is where pi squared makes a big difference, because of the mathematical nature of the infrastructure. So everything ends up in a mathematical proof. And that at least gives us assurance that mathematically speaking, that computation is correct. And now we only have to worry about the other aspects that we handle just as well as blockchain. So those are highest level of assurance, but we also eliminate the correctness concerns with respect to the programming language, meaning semantics. And then finally, and most importantly, you mentioned scalability limitations. Well, so, the blockchain trilemma, that you cannot have scalability while at the same time decentralization and security. Well, we can. In the pi squared approach, because in the fastset in particular, fastset protocol, because it is not a blockchain. That is a trilemma for blockchains. Scalability is a problem for blockchains, but not for other decentralized distributed infrastructures like Facet. And we can go into more technical details there, but the main takeaway is that Facet enables massively parallel settlement. So not only verifiable settlement, but also massively parallel. And the reason this can happen is because Facet drops the sequentiality requirements, the chaining requirements that blockchains enforce. All right, so verifiability trumps sequentiality, let's put it this way. So if something is verifiable, and that's all you care about, is it verifiable? Is it true? Is it verifiable? Yes, that's what it matters, not the actual total order, not the actual execution. For example, take voting. Okay, you and I vote. All it matters is that we vote before a certain deadline, right? Not the fact that you voted before me or I voted before you. Nobody cares about that. Or payments, when you pay somebody and I pay somebody else, all it matters is that we paid, and that's verifiable, but not who paid first. Okay, so we found that more than actually 90%, we did a thorough analysis of all the transactions on Ethereum, and more than 90% of them are actually not in need of a total order, right? Voting, escrows, payments, NFTs, all kinds of tokens, digital assets, moving them around. None of those require a total order or a chaining or a blockchain for that matter, which means that we can massively speed settlement, still staying decentralized, verifiable, and secure if we drop the chaining total ordering requirement. So that's how we address scalability.
This is all really fascinating, and you delve into the mathematical side of it, and I just wanted our audience to sort of get a sense or flavor of your background and who you are and the academic side of what you bring into building PySquare. So if you don't mind, could you just share just sort of like...
Yeah, certainly, glad to. So as I said, now I'm a professor of computer science at University of Illinois, Urbana-Champaign, and my specialty is programming languages, but I also teach distributed systems and formal verification and software engineering. So everything that is related to correctness and assurance of systems. And previously, I was a research scientist at NASA Ames in California, close to Stanford. And I spent a couple of years there right after my PhD. I got my PhD from University of California in San Diego. And before that, I did my bachelor's in mathematics and master's also in mathematics, foundations of mathematics, back in Romania. I'm originally from Romania. I came to the United States in 96, and I've been here ever since. And as I said, I was always interested in using mathematically grounded techniques, which we also call formal methods, to assure the correctness and the trustworthiness, to say so, of computing systems. And in particular at NASA, I was directly involved with proving correctness of navigation software. For example, I worked on tools that catch navigation inconsistencies. I probably know that there are some accidents at NASA due to incongruence of measurement units. Right? So some teams use the metric systems, others use the British system, and you cannot add 3 feet plus 5 meters and get 8 watt, right? So there are some errors like that, and we developed tools that would guarantee that the program does what it's supposed to do. And then what I've done, I brought all these to blockchain. So Runtime Verification is the first company that I founded back in 2010, before blockchain was a thing. And our clients back then were NASA, Boeing, Toyota. And what we did was to use these mathematically grounded techniques to prove mission critical or security critical, safety critical software correct. And then in 2017, we started doing security audits in the Web3 space, blockchain space, for Ethereum, Cardano, and many other blockchains, Algorand, Tezos. Yeah, so we've seen all the misery in this field, all the bugs, all the types of categories of bugs, the vector attacks. And then we created Pi² from scratch to address all these problems and to essentially build a new foundation for Web3 right, the way it should be, to build it right and the right foundation.
Hey everybody, quick thing here. We're excited to announce WAGMI Advisory, your home for all things fundraising, hiring, and partnerships. This is all about supercharging your project with the WAGMI network, consisting of over 20,000 executives, investors, and builders in crypto, all ready to come alongside your project to help it succeed. Get in touch at team@wagmiventures.io to learn more and figure out if WAGMI Advisory is the right fit for your project. Let's get back to the show.
Yeah, no, as you pointed out, you worked at NASA and your work involved formal verification for mission critical systems like spacecraft navigation. How did that experience, which is pretty high stakes because they're essentially lives on the line. Yeah. So how did that experience shape your approach to building a trusted system like Pi²'s FactSet?
I think the answer is very simple. We take correctness. Many would say that we take correctness very seriously. No. For us, correctness is not negotiable. It's paramount. Okay, so everything must be correct. So our techniques are what we call correct by construction. It means that you cannot even do one step of computation unless it is correct with our tools. Of course, the problem with that is that things are slow initially, or the whole process is a bit slower because there is more to guarantee, more to prove, more to ensure. But once you engineer the framework that allows you to do things correct by construction, then the only thing left is to optimize it, to optimize performance. And this is something that we humans, again, are very good at. We are really very good to optimize and to make things fast once we understand what we are doing. And that's what we've done. That we designed the algorithm, the whole protocol. We designed the execution infrastructure, the verification infrastructure, with semantics-based principles of correctness first principles. Correctness, again, is non-negotiable. And the only thing left was, again, scalability and performance. And we recently reached very good performance numbers. I don't know if you heard that, but we managed to achieve more than 100,000 transactions per second at this point on the FactSet network. So 100,000 plus TPS, where everything is verifiable and correct by construction. So nothing to prove, nothing to worry about. Secure, fast, and correct. I like to say, and I teach my students that way, that is a consequence of a right architecture and the right design. When you do things right from the beginning, you may do them a bit more slowly than others who prioritize speed, but long term, you achieve higher speed. Because once you prove that things can be done independently of each other, then you can execute them concurrently and you can get higher performance. If you just try to get performance, you are not sure if you can parallelize the execution, then to be safe, because otherwise you run into very, very bad errors, then you sequentialize just to be sure. But once you prove correctness, then you can parallelize, and that's how you get efficiency. So in our case, right now, FactSet is what we call in distributed systems, it's embarrassingly parallel. Embarrassingly parallel means that every single transaction can be executed completely independently and in parallel with the others. Nobody has to stay in line for nobody else.
Yeah, no, congratulations on 100,000 TPS. I think you and I had worked and I saw a little demo, a little taste of how fast it is.
Oh, right. I showed you a demo. Yeah. Great. I remember. Yeah.
On the wallet transfer we did a few days ago.
Yep. Exactly. That's what you feel. So instantaneous transactions. And more importantly, all those transfers that we made to each other, they looked fun, but the reality is that there are no blocks and no ordering. At the same time, there could be another 100,000 guys, making transfers to each other. And nobody would be in a block or in a sequence because you don't need them. So why force them? Why enforce an artificial sequence when you don't need it?
And just even speaking on sequencing, another thing you have challenged is the necessity for layer 2 solutions. I think you've argued that if a layer 1 or pi square as it is implemented with verifiable computation, then L2s would automatically be obsolete. Can you
or L1s, depending on how you look at it. So the reality is that the reason we have L2s, I mean, let's just be honest. The reason we have L2s is because L1s are not good enough.
That's right.
Okay, if L1s, now imagine that an L1, take Ethereum. Imagine that Ethereum could do like 100,000 TPS. Okay, and it would be very fast and latency, let's say 100 milliseconds. Probably would have no layer 2s whatsoever. Probably would have no other blockchains either at this point. Why? Right? Because it's so fast. But because they are slow, because of the scalability, part of the blockchain trilemma, now we have L2s. But now imagine that you have a framework where every computation done by an L1 or L2 becomes a claim that comes with a proof, and that proof is instantaneously verifiable, right? So you can now settle that claim or transaction instantaneously because there is nothing to check because it's been checked already. Everything has been proved. Then why would we need to make a difference between layer 1s and layer 2s at all? No, you wouldn't. There are some interesting questions there, where is the programming language? Is it settled? Who vouches for it? And all those can be addressed, and actually can be addressed a lot more cleanly than, in the interplay between layer 1s and layer 2s today. And then once you do that, then you realize that there is absolutely no difference between L1s and L2s, and they can both be settled at the speed of light. And blockchain itself, which is a total order, literally, that's it. That's what a blockchain becomes. For Facet become a blockchain is a sequencer, essentially. So all of these are just, sequencing transactions, and there is no need for a difference between them. So that's why I said I'm not saying that layer 2s are not necessary. I'm saying that there is no difference anymore between layer 1s and layer 2s. And they all become contracts. Actually, on Facet, a blockchain, you can very easily deploy a blockchain on Facet. Actually, we are doing it currently with our friends at MegaETH. We have a partnership with them. We'll announce more details soon. But essentially, we take every single block produced by MegaETH and verify it and turn it into a claim and settle it on Facet. And the benefit of that is that now MegaETH can claim, if it wants, instant finality or nearly instant finality. Takes a few hundred milliseconds, but that's it, as opposed to 7 days, right? As in optimistic rollups. And now stepping back even further, what a blockchain really becomes, besides a sequencer, it's also just an execution layer. You execute some block, and the faster you execute it, the faster you can produce the claims that need to be verified and settled. But the beauty of having a massively parallel infrastructure like Facet is that now you can verify all these blocks in parallel. Okay, so you can produce blocks at 10 millisecond, let's say, intervals. 10 millisecond is amazing, and MegaETH, by the way, achieves that. That means 100 blocks per second. No problem. You can verify all those 100 blocks per second in parallel. And suppose that it takes 1 second to verify a block. It doesn't. It takes half a second, actually, currently with our K verifier. So in half a second, you verify 100 blocks. So all you do, you add half a second latency, right, to the network. And once you have that, stepping back even further, you say, why do I even need the L1? Because the L2 is already an L1 now. It's a blockchain. It's settled, it's verified. So why do I need an L1 again? Why do I make a distinction between L1s and L2s again? So we are very, very, very positive, very bullish on MegaETH. We believe that they have the best EVM technology around, execution technology around, and we do our best to help them become the EVM based blockchain of choice, and strongly recommend them. And they will be not only super fast, but also verifiable and nearly instantly final, thanks to the integration with Facet.
Yeah, and I'm happy you actually bring up the speed, the finality, and how Facet is helping them to achieve that. This is all coming from, and I think you mentioned this as well, the K framework, which you co-created, and that's a cornerstone of PySquared's technology. We've touched on Mega ETH, but are there any real-world examples of a programming language or a smart contract that has been made more secure or efficient because of the K framework?
Oh, lots of them. So basically, I invented the K framework when I was still at NASA. That was early 2000. I think the first paper was published in 2003. And I developed it in my research lab at the University of Illinois with my postdocs and doctoral students. And in 2010, actually 2012, we brought it to runtime verification first. And then it was developed by many engineers there. So probably at this point, there is more than 100 man years of engineering, research and engineering put into the K framework. And many languages have been formalized in the K framework, meaning that they have been defined mathematically, have a mathematical theory that defines Java or C or EVM or Solidity or Rust or WASM and so on and so forth. And once you do that, now you can reason about programs using mathematics, including about executions of programs. And in the Web3 space, actually, the K framework has been used, and runtime verification was hired by the Ethereum Foundation on several occasions, and not only to formally verify critical contracts. For example, the first version of Uniswap was formally verified using the K framework. Then the Ethereum deposit contract, if you remember, when Ethereum migrated from proof of work to proof of stake, there was a contract, the deposit contract, that allowed you to transfer your ETH from proof of work Ethereum to proof of stake Ethereum. So that contract was critical, and because if that had bugs, then you can lose your ETH, literally. And that was also formally verified using the K framework. So that's among many other protocols. If interested, you can go to runtimeverification.com and look at the various projects that have been formally verified using the K framework. But what is less known about the K framework, and in general about language frameworks, is that they are good not only to prove mathematical correctness with respect to certain properties of programs, but also to prove executions of programs. So I execute a program and I can prove it mathematically correct with respect to the definition of the programming language. In the Web3 world, when people say prove, they usually mean cryptographic proofs using zero-knowledge technology. But in the world of formal methods, when we say prove, we mean mathematically proved. And mathematical proofs are much more rigorous and obviously correct than the zero-knowledge proofs. Zero-knowledge proofs are pretty buggy, actually. And then what we do, we generate a cryptographic proof from the mathematical proof. So anyway, I can talk forever about the K framework, so please let me stop here.
No problem. I might actually get you going again on another term and concept that you created while you were at NASA. Again, you alluded to this is runtime verification. And looking back at your time at NASA and how far you've come in sort of the blockchain Web3 space, like, I'd be curious, like, what is the most surprising application of runtime verification you've seen, whether it's in aerospace or blockchain?
I think the most amazing application was still at NASA. That's what amazed everybody and made runtime verification be broadly accepted as a field of science in formal methods. Was when we proved that you can formally verify a very complex system by actually avoiding the complexity altogether. So it is well known that it is very hard to formally verify systems because you have to model every single computational step in the system mathematically. But here is another way to do it. And that's what runtime verification proposed. Said, how about this? Let's not worry about verifying the complexity of the actual system, but instead, let's monitor, let's observe the system, let's observe what the system does. And let's make sure that we do not let it go wrong. Okay, so we observe what it does, we know what it is supposed to do, that's what the formal specification of the system does, and then you know that if you observe it and you correct it, you steer its execution whenever it does something incorrect, then all you have to worry about now is that your recovery code is correct. And that is much, 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 much simpler and smaller to analyze, to verify than the actual system. And that was so surprising. We use it in several instances at NASA with controllers of spacecraft, right? You have a controller which is super optimized for certain things like, navigation, let's say, but not necessarily for certain other aspects. And you can just monitor it. And as far as the aircraft stays within the stability, it's called the stability envelope, then you let it go. You don't care exactly where it is. That was super, super interesting when we first came up with that principle. So basically it turned out that you don't need, you can completely skip the complexity of the system and still guarantee that it is correct, but differently. Now, fast forwarding, we apply the same principles now, even in pi squared. What I told you before, that we execute a program, generate a mathematical proof, then verify the mathematical proof. That's exactly the same principle, but pushed to extreme. Okay, so I observe the program by looking at every single step that it does according to the formal semantics of the programming language. I don't care about the compiler, I don't care about the interpreter, I don't care about the bits, inside the memory or inside the chip or registers. All those are just a means to take the program step by step through its mathematically abstract states. And all I have to do is to verify as the program executes at runtime, so to runtime verify the execution of the program. And as far as it falls into the correctness of the mathematical universe, the execution is correct. Okay, so the same principle, but now 20 years later, used in I was about to say blockchain, but it's not blockchain, it's Web3, because I truly believe that Web3 is here to stay, while blockchains, not necessarily. I mean, blockchain may stay, but for certain applications, they require total order, but they will not stay the central piece of Web3.
Yeah, I think there certainly will be some evolution there. And as we sort of talk about some of the other technologies that connect here, one of the emerging techs that we discuss on this show is AI. And there's a lot of your work that bridges blockchain and AI and brings this all together. And in many ways, we're seeing the blockchain evolve. So I wouldn't say disappear completely, but Web3 here to stay, blockchain still evolving. But as you see all these fields converging, what role do you see PySquare and your work generally playing in it?
Yeah. So maybe I was a bit too harsh saying that blockchains will not stay. I think many of the technology that blockchain brought will stay. This idea of having accounts and having, protected by private and public keys, having assets in these accounts, transferring the assets, people owning the assets, and many other components, modules of blockchains will stay. But what I think will not stay central as a central piece of Web3 will be this idea of total ordering and sequencing of the entire universe. Okay. Because nature is not like that. We learn from nature, right? In nature, things happen in parallel and they cannot be sequenced. Take all the leaves in a tree, when they are blown, in a storm or in a wind or even in the breeze. Nice calm, beautiful breeze, right? So all the leaves move at the same time. It would be really silly to even conceive that there is a total order, in how they move. Right. So, but getting back to your original question, how formal methods, blockchains, and AI come together. So formal methods are really all about using the mathematically grounded universe of knowledge in order to reason about things. And those things can be blockchains and AI in particular, but many other things. Blockchains are definitely very useful for, or currently blockchains are still, many people consider Web3 equals blockchain equals crypto. That's fine for now. So blockchains are important because they provide cryptocurrencies, and AI agents need cryptocurrencies. Because how else can they pay each other? Maybe we don't want to call them cryptocurrencies. We call them digital assets, digital money, digital something, numbers, tokens. But they need to pay for services and to pass to each other services. So that's, and you want that to be verifiable and decentralized and to have all the good features of blockchain. So all those are definitely needed, and formal methods are needed because you want everything to be correct in the end, provably correct and verifiable. Right. So all these are great together. The only problem again is the sequencing part of blockchains, because that's what stays in the way of scalability. Very soon, we will have millions of agents. Humans will have several agents working for them at the same time. We are billions of people. There will be billions of agents. And now imagine that these billions of agents want to do micropayments or to transfers of things, messages to each other, to communicate with each other. So suppose that you simply have, now I'm super, super, super conservative, right? Suppose that you have 1 million messages only or transactions only that 1 million agents want to do in a second, right? So at the same time, 1 million agents will want to do something, right? You have 1 million, you need an infrastructure that can sustain 1 million TPS, okay? Even with the fastest blockchains today, take Mega East, 20,000 TPS. 20,000 TPS would be in 50, I don't know, seconds or more, 50 seconds, right, for 1 million TPS. So basically, all these agents will have to stay in line. You'll have to wait 1 minute, right, for your air ticket to be bought by your agent. That's ridiculous. And only as an artifact of the blockchain infrastructure, right? Because your agent buying your ticket has nothing to do with Joe's agent, I don't know, returning a book or sending a book to somebody else, right? So it would be, it's literally silly to even conceive that a total ordering is needed for AI. Maybe needed for each AI or for a small group of AIs that do a collaborative task. You have the so-called causal dependencies between messages, which can very well handle using well-understood techniques in distributed systems. But what I'm getting to is that blockchain is not necessarily the best structure for this. And if Web3 and AI are here to stay, and I think they are here to stay, then blockchains may have to give something. And I think they will have to evolve. That's the truth. They will evolve in structures that will be massively parallel. And if you need the total order somewhere, then you have a smart contract that does exactly that. But that's just as well an app chain. We're talking about no difference between L1s and L2s once you have the right infrastructure. I would say I would also add app chains to the soup. There will be no difference between an app chain and a layer 1 or a layer 2. They'll do the same thing. They just, for a particular domain, they will enforce a total order on actions.
Got it. Wow. This is, as I think through the convergence of these techs and what you've built so far, also thinking of what Facet has been delivering. I know that you're either planning or maybe looking to recently to launch the testnet of Facet. In how these fields and these technologies emerge, is there any one particular feature or capability that you're excited to see developers experiment with Facet?
Yeah, so we are going to launch, if everything goes all right, we should launch should pre-release, let's say, our testnet on August 12th. So that's a few days from now, a week, less than a week. And what it will demonstrate is the most common capability of blockchains, which is that of doing payments or transfers, asset transfers, token transfers. So users will have a wallet and they can do transfers to each other. There is also an RPC for those more adventurous users, developers. They can write scripts and programs and do it programmatically. But what we will demonstrate, and I would really, really, really like every dev trying it to look at this, is the amazing performance TPS. We are aiming for 100,000 TPS. Maybe we will not have 100,000 from day one, but let's say we'll have 40,000, 50,000, even 40,000. That's twice faster than the fastest layer tools. Okay. So yeah, so that's the exciting part. Because I believe that once users, once we humans realize that we can do all these transfers that imagine in only 15 years ago, Bitcoin, right? So it took 10 minutes for a transfer, and now we can do it, in less than 100 milliseconds. And we can do 100,000 at the same time, as opposed to, 15 in a second. That's how much the Web3 technology evolved in 15 years. And I would like every single user and developer trying our network to first convince themselves that this is true, that you can indeed achieve this amazing performance, and then reflect, maybe get a nice drink, coffee or water or beer, and reflect on what's going on here. How performance is not the problem of Web3 anymore. It is the problem of, what I'm going to say, it's the problem of blockchains, not the problem of Web3. We can have verifiable, secure, and very efficient, infrastructure for digital assets and transfers.
Wonderful. This has been a really good conversation. And before we wrap things up here, it would be great to hear, what else in crypto and AI excites you.
I think AI, from a crypto perspective, will boil down to two important capabilities or features that are needed. One is the capability to do micropayments or digital asset transfers at lightning speed and dirt cheap, because agents will do eventually hundreds, maybe thousands of these per second, and you cannot afford to pay for this more than 1,000th of a cent or something like that. So so the price should be really low, and blockchains, of course, cannot sustain that because they're expensive by their nature, because all validators need to achieve consensus and so on. There's a lot of communication, a lot of computation going on. So that's one aspect. Payments, micropayments that are needed for AI, much more than humans need them. And then the second one is the inference. We want verifiable inference and then settle that inference, right? So if your electric car, your AI-powered car, decides to take left automatically, in an intersection, you want to make sure that it used the right inference, the right model with your data, and not, somebody wanting to kill you, And so that's why everything that AI will do for us, I think in the near future will be verified and settled. Networks like Fast are absolutely perfect for that, because again, all agents can do their thing, whatever their thing is, inference, of course, but payment or settlement of that, they can do the settlement at the speed of light, completely independently in parallel with all the others. So I'm not an expert in AI in particular, like in LLMs and the particular learning, algorithms and techniques, but very few people really are. Most of us are just users of AI. So from that angle, I cannot say what is really exciting about AI innovation at the algorithmic level, but I can say that at the level of using AI and having AI agents do work for us, I think we must have an efficient, super efficient infrastructure, optimal infrastructure for micropayments and for verifiable settlement of inflows. That's what excites me.
Awesome. Thank you so much, Grigore. This has been wonderful. You've been really generous of your time and your insights here. And we really look forward to seeing what comes out of your testnet and your eventual launch. Congratulations on your partnership with Mega ETH. I know there's much more that you're going to be announcing very shortly, but thanks for being on the show and we'll see you soon.
Thank you so much, Benga. Nice talking to you and greetings to your audience.
Hey, everybody. Thanks for listening. If you enjoyed the episode, go ahead and give us a good 5-star rating and subscribe wherever you're getting your podcasts so you can get all the latest conversations from the most interesting founders, builders, and investors from across the world. Thanks so much and have a good one.